Hey students, so we're on 4.7 and today we're practicing sketching graphs, something you know about already, but we're going to learn some more advanced techniques. So as normal, let's begin with a warm-up. I want you to pause the video and have the best go you can at sketching the function on the board. 4x squared minus 4x plus 1, all divided by x squared minus 1. Use all the skills you already know, no calculators, no technology, to sketch it as best you can. Give yourself 5 minutes, then restart the video. Okay, so you've had a go at sketching this function. We're going to build up to this in stages by looking at some slightly more basic functions and then getting closer and closer. But throughout all of this, whenever we're sketching functions, Desmos is our friend. And I'm going to come back to Desmos a few times as we do this, but here you can see the function that I asked you to sketch. So you'll know straight away how close you got, whether your key features match those on the graph here. But let's instead go to our notes and start at the beginning. So, with all the questions we do today, I want you to follow this idea that there are 4 things we always need to determine information about before we begin our sketches. So you could have a guess about some of these, but the key things we're always going to think about are, do we know anything about the intercepts, x and y? Do we know anything about asymptotes? And we're going to look at non-vertical, non-horizontal asymptotes, as well as ones we're really familiar with. The third thing will be stationary points, places where the gradient is equal to 0. And the final thing will be points of inflection, where we're able to identify that the second derivative, d2y by dx squared, is equal to 0. So it says at the top here, what we're going to be sketching are rational functions. And it's worth us defining what that means. What is a rational function? Well, it's p of x over q of x, where p of x and q of x are both polynomials. And one thing we should just say there is, it's something that can be written in that form, but it might not be exactly in that form. So for example here, f of x equals 8x minus 3 plus 2 over x. Well, we can write that in the form p of x over q of x, because we can say that's the same as 8x squared minus 3x plus 2 over x. So p of x is 8x squared minus 3x plus 2, and q of x is just x. And both of those are polynomials, a string of finite powers of x with real coefficients, and so we can work with them. It is a rational function. It's included in what we're talking about today. The second thing to notice is going from this p of x over q of x form to different forms like the one that was given here can tell us something. And actually, we're going to jump straight in by talking about asymptotes. So hopefully we're used to this idea of x tending to infinity, either positive or negative. In other words, x getting really, really large. And if we look at x getting really, really large, in this expression here, we can see that the 2 over x, this bit, well, that's going to disappear. So if x tends to positive infinity, well, what's going to happen here is this last term, the 2 over x, that's going to be positive and really, really small, getting smaller and smaller and smaller. So what that means is f of x is going to tend to, it's going to get closer and closer to the other bit, the 8x minus 3, because the 2 over x is going to disappear. So f of x is going to get closer and closer to 8x minus 3 from above. Why from above? Well, it's always going to be equal to that, but then plus an extra small positive quantity. And it's worth us noticing that we know it's going to come in from above, because the reverse is as x tends to negative infinity, the same apart from the last term is going to be small and negative. So f of x tends to 8x minus 3, but this time from below, because the extra little bit you're adding on is going to be negative. What does this look like? Well, we're going to come on to this idea pretty soon, but if I have the graph 8x minus 3 and some kind of coordinates, what we could say about this graph already is it's going to tend to that line from above when x gets large, and it's going to tend to that line from below when x gets small. So we don't know what happens in the middle here, but we know the behavior for very large x, both positive and negative. And our name for this line, 8x minus 3, is a non-vertical asymptote. Okay. So I guess this is like trick 1, and I might label it there, trick 1. The x tending to positive and negative infinity. Trick 2 is what we're going to look at down here. It's this idea of adding together known functions. And we're going to look at an example. And what I'm going to say for all of the questions we're going to do today is, unfortunately, I wish I'd given you more space. So you're going to have to write small. And for that reason, I advise if you're going to have your own go at these questions, definitely do that. Pause the video and try it before we go through it. But do it on a scrap piece of paper or in your workbook. So, trick 2. Trick 2 is when we can easily break the rational function we're given into two parts, g of x and h of x. Because what we can then do, if g of x is easy to plot and h of x is easy to plot, we can plot both of those and then just look at adding the y coordinates. And the technical term for the y coordinates here is ordinates. Don't worry too much about that, but that's what it means, the y coordinates. So we're going to do this example here, and the first thing I'm going to do is just change it slightly. There's a bit of a typo. I only want it to be x plus 1 over x. The reason being that x squared plus 1 over x is very similar to the example we're going to do next. It would definitely be possible to do it this way, but we're going to stick with x plus 1 over x. So if you want to have a go at this yourself, pause the video, try it in your workbook, a sketch of this function using these 4 things, and if not, I'm going to go through it in 3, 2, and 1. Okay, so first thing I'm going to use is this trick 2. I should have labelled it, shouldn't I? Trick 2. They're adding 2 functions. Because it's already done for me here, I can see that f of x is x plus 1 over x. So g of x equals x, h of x equals 1 over x, and f of x, well, that's g plus h. So that's telling me quite a lot already. If I'm going to do small sketches here, not my final thing, but a small sketch, what I know is that, well, y equals x, that's easy to plot, that looks like this, and y equals 1 over x, well, that looks like this. And then what we can do is for every value of x, I'm just going to add on the 2 values from g and h. So I can see in the top right quadrant they're both positive, so I'm going to stay up here. And in the bottom left quadrant they're both negative, so I'm going to stay down here. And I can see that there's going to be some symmetry. What I can see is this graph is very small here, so I'm going to be very close to the other one, to the reciprocal function. Then I'm going to get further away. This point here, I'm double the height. And then as time goes on now, I'm going to actually, because the 1 over x function gets smaller and smaller, I'm going to get closer and closer to the line y equals x. And so actually we can regard both of these other functions, g and h in this case, as being like asymptotes. I've said this is a small function. This gives me an idea of the shape, but I want to do a little bit better than this. I want to think about intercepts, asymptotes, stationary points, points of inflection. So let's think about intercepts first. This sketch is suggesting to me there are no intercepts, but let's check that. Intercepts. I'm going to get an intercept if x plus 1 over x equals 0, but that would imply that x squared plus 1 over x equals 0, which would imply that x squared equals minus 1, which is impossible. Therefore, no x-intercept. And the x equals 0, if we look at the domain here, is not in the domain, so no y-intercept. So I know that my function should not cross any of the axes. Second thing we're going to look at is the asymptotes. Well, I definitely have an asymptote which is x equals 0, because this function is undefined for x equals 0. So x equals 0 is a vertical asymptote. But actually, what I've already done here tells me that I have this 1 over x function which is going to provide that asymptote, and of course as 1 over x gets closer and closer to the y-axis, this function is going to get closer and closer to that, and so it's doubling up. We can see that asymptote in one of two ways. And the other thing we're going to say is we're going to say, well, what happens as x tends to positive infinity? X gets bigger and bigger and bigger. This second term, the 1 over x, is going to vanish. It's going to get very small. So y will tend to x from above, because we're adding on that small extra amount. And as x tends to negative infinity, y is going to tend to x from below. And indeed, that's what we see with our little sketch, that we're expecting to get closer and closer to it from below. Third thing I'm going to look at is the stationary points. So I'm going to differentiate. Probably the easiest form to use is the form where we split. So f of x would be 1 plus, differentiating 1 over x would be minus 1 over x squared. The gradient being 0, well, that implies that 1 minus 1 over x squared equals 0, or in other words, x squared minus 1 over x squared equals 0, or in other words, x equals plus or minus 1. So I'm going to have stationary points where x is plus or minus 1, and then substituting that in, if x is plus 1 into my function, I'm going to get 1 plus 1, which is 2, and if x is minus 1, I'm going to get minus 1 plus minus 1, which is minus 2. So I have stationary points at minus 1, minus 2, and 1, 2. And then the final thing we look at is the points of inflection. So, looking at points of inflection, f double dash of x, first term differentiates to 0, but the second term is going to differentiate to 2 over x cubed, which cannot be equal to 0, so no points of inflection. Meaning that actually I think we've got lots of information now to help me plot this graph and have a pretty good stab at it. I'm going to carefully draw in my line y equals x. and then my function is going to look something like this, symmetrical. This point here, my maximum -1, -2. This point here, my minimum 1 and 2. And labeling this line as y equals x. This is my finished sketch of that function. And if I just go back to Desmos quickly, I draw on the line y equals x, and then I add in the function we're talking about. I can see it's pretty close. So yeah, Desmos is your friend. Use it regularly when trying all these questions. Okay, plenty to do today, and I don't apologise for that. Loads of practice. The next graph I want you to look at is this one here, x cubed plus 2 over x. The domain excludes 0 again, and I'd like you to have a go at this yourself. Pause the video, use all those strategies we just did, and then I'll go through it with you. Okay, I'm going to go through it in 3, 2, 1, and 0. So, kicking off here, I'm going to do my 4 stages, and I'm going to look for intercepts first. So the first thing is x equals 0, not in domain. This doesn't always happen, but we've got to be aware when it does. Therefore, there's going to be no y-intercepts. Then we need to think, okay, when is f of x equal to 0? That implies that x cubed plus 2 is equal to 0 for the numerator. So x cubed equals -2. So x equals minus 2 to the power a third. Sorry, I just wasn't sure about exactly how I was going to write that then. So minus 2 to the power a third. That's going to give me 1 intercept only. Okay. Number 2, let's think about asymptotes. Well, the first one, x equals 0, is an asymptote. And then we're going to look at this idea of x getting really large, and to do that we're just going to split the terms like we've done before. So I'm going to get x squared plus 2 over x, and I'm going to think as x tends to positive infinity, f of x is going to tend to, the second term is going to vanish, get really small, but it's going to be positive. So this is going to tend to x squared from above. And as x tends to minus infinity, same thing, but because the second term is now negative, it's going to approach x squared from below. This is all good stuff. Now I'm going to look at my stationary points. So my split term here is probably the best way to go. If I differentiate this, I'm going to get 2x minus 2 over x squared. And f of x equals 0. Well, that's going to happen, if I combine this again, that's going to happen when 2x cubed minus 2 equals 0. Looking at this, it's one fraction and the numerator, which tells me that x cubed equals 1. So x equals 1, the only solution for that. And substituting x equals 1 into the equation is going to give me, I believe, a y coordinate of 3. So 1, 3 is a stationary point. And in fact, I could strengthen that and say it's the only stationary point. And then for number 4, if I look at points of inflection, fourth ingredient, f double dash of x, using the split terms is easiest, 2 plus multiplied by minus 2, 4 over x cubed, and that is similar to before. This is not similar to before. This actually would have a 0, because if I write this as one fraction, this is going to be 2x cubed plus 4 over x cubed. So the second derivative being equal to 0, well, that's when 2x cubed equals minus 4. So x equals the cube root of minus 2. So that's minus 2 to the power of 1 over 3. And look, notice that's the same as my intercept here, which is an interesting thing. So as I draw it, I can draw a point of inflection at the intercept. Then the final thing that can help me before I do my final go at this is just to use this idea of adding ordinates. So in my split form here, I've split it into y equals x squared, which looks like this, and y equals 2 over x, which is a reciprocal, just like the other one we looked at. And so as I think about, well, what's going to happen is you add both of these. The right hand side is a similar shape to what we've had before. It's going to look something like this. It's always going to be above these two, because they're both positive, and it's going to tend towards both curves. But for negative values of x, we get something different, because one of these is positive and one is negative. The graph is actually going to, when I add them, I'm going to get the midpoint of them. So the midpoint of both of these may look something like this. And in fact, that shape, so our shape is very similar to what we're looking at here. So let's do a big version of that. Include all the information we know we should. So asymptotes first. I've got the y-axis, and then I also have my quadratic y equals x squared. I've got an intercept at minus 2 to the power a third. Which is also going to be a point of inflection. And then I have a stationary point at 1, 1, 3. And then using the idea that we have an asymptote here and the shape that I've got above, there's my minimum. Then I'm going to get closer and closer to y equals x squared. Here I need to be close to y equals x squared from below. And then as I come through here, I have to have a point of inflection and get closer and closer to the axis. So using the work that I've done, it has to look something like this. And in fact, if we go back to Desmos, I've got my two curves. And if I add on the one we're looking at, indeed it does look exactly like we expected. So our method of looking at those four things, the asymptotes, the intercepts, the stationary points, the points of inflection, works a charm. Okay. Quick look at trick 3, then I'm going to give you one to do yourselves. So, trick 3. Is to use an idea that we have seen before, and it's this idea of reciprocals of known functions. And we used this when we were plotting our reciprocal trig functions, or circular functions, so sec, cosec, cot, etc. Because if ever we can write a function f as 1 over q, where q is just something we know, well then we can use this, what did we call it? A funhouse mirror method for sketching reciprocal functions. So it works for circular functions, and we can use it here. So we're going to look at an example of that, but as we do our example, let's just think about how this works again. Well, the x-axis intercepts are the original function, so the zeros. Well, 1 over 0 is infinity, So this must give us the asymptotes for the reciprocal function. We know that the reciprocal of a positive number is positive, so we stay above the axis, and the reciprocal of a negative number is negative, so we stay below. We remember that a graph and its reciprocal, well, they have the same value when that value is either 1 or minus 1. Because 1 divided by 1 is 1, 1 divided by minus 1 is minus 1. So 1 and minus 1, and the reciprocal doesn't change the value, or has the same value as the function. If we've got a maximum of the original function, well then the reciprocal must be a minimum, so those reverse. And in fact, if one is going up, or the gradient is positive, the other must be going down, the gradient is negative. So those are our rules for how this funhouse mirror idea works. And so let's try it with one here. Pause the video, and then in your workbook, have a go at sketching 1 over x squared minus 4x by first thinking about y equals x squared minus 4x. Pause the video, have a go. Okay, this one's a quick one. So this trick, if we can use it, is really effective, because all I'm going to do, and I can do this every time, is just draw on here the axes and then the lines y equals 1 and y equals minus 1. And then the function that we're going to look at, the q of x in this case, is x squared minus 4x, which we're very familiar with. That's x minus 4. So it's going to have, if I do this in green, it's going to have an intercept here and an intercept at 4. The midpoint is going to be at x equals 2. X equals 2, this is going to be 2 squared minus 8 and minus 4, so down here. And so my quadratic is going to look something like this. Just notice, whilst this isn't complicated, it's important to get this to work out that this minimum is below the line y equals minus 1 rather than above it. That's critical to the shape. If this is above the line y equals minus 1, we get a very different shape. So we do need to work out this y coordinate here. This is 2 minus 4. And then once we've got this, we can just do this funhouse mirror idea. So zeros become asymptotes. So I must have an asymptote at x equals 4 and another one at x equals 0. I'm going to go through the points where our function crosses and crosses the y equals minus 1 or y equals 1. And then apart from that, I'm looking for the reciprocal value. So a funhouse mirror. All these values that are so large, they must be really small here. And then I have an asymptote. Similar thing going on here. Really quite steep. And then underneath, I have the asymptote. Must be negative. And then I never cross this line because I never reach a positive value, never get to infinity, there's no asymptote. So as I sketch this, the only thing that must happen is that I must come around and then down and back to this asymptote, and I can work out the value of the maximum there. The value of the maximum, well, it happens at 2, and then it's the reciprocal of minus 4, so it's minus a quarter. And that graph, this method, this trick, gives us a way of plotting this without having to go through the lengths that we went through with the previous examples, because we can have confidence in this. Indeed, if we have a look at it, here we go. Here are the lines that we drew on there. Y equals minus 1, y equals 1, and the original quadratic. If I add in the one we're interested in, we can see it matches the diagram almost exactly. So, a very good trick to help us with these types of questions. Okay. a couple more. Hopefully we're getting the hang of this now. Here we are at the one that you started at the very beginning. And what I would like you to do is, if you feel like you've given a much better shot now than you did at the beginning of the lesson, then pause the video again and try it once more, see how well you can do. Otherwise, we're going to analyze it together using our 4 key tools. So pause the video, have a go. Otherwise, I'm going to go through it in 3, 2, and 1. Okay, so a big question and plenty to bite off. So let's jump into it. Intercepts. This time it's undefined on the whole domain, all real numbers. So the first thing I can do is go, well, what if x equals 0? If I substitute in x equals 0, I get 1 on the numerator and minus 1 on the denominator. So y equals minus 1 is the only y-intercept. And then we're going to look at the numerator being equal to 0. So in other words, if y equals 0, well then the numerator is 4x squared minus 4x plus 1, and I can actually see that that factorizes as 2x minus 1 squared. So if this is equal to 0, then x must be a half. So it looks like I've got one y-intercept and one x-intercept. Okay. Asymptotes. The split form is, well, let me get onto that. First thing, that if the denominator is equal to 0, we know we have a vertical asymptote. So that's going to be the case for some values here. Vertical asymptotes at, when the denominator is equal to 0, that must be x equal plus or minus 1. But then for non-vertical, we have to think a little bit more carefully. So f of x. This is what we call an improper fraction, because the degree of the numerator is the same or larger than the degree of the denominator, meaning that we can do a division to simplify it. And the coefficient here is 4, so I know that I must have a whole number being 4. 4x squared divided by x squared is just going to give me 4. It's a nice little trick. And then I'm going to have plus something over x squared minus 1, the remainder from the division. And a little bit of a shortcut here. If I were to look at what I've got here and to try and represent it all over a denominator of x squared minus 1, I would multiply 4 by x squared minus 1. The 4x squared term will match, that's what we were expecting, but then I'm also going to get a minus 4. But I don't want minus 4 on the numerator, I want minus 4x plus 1. So what I must have here is a minus 4x. I want it to be plus 1, but I'm actually going to have a minus 4 from multiplying the 4 by the minus 1 here, meaning that I need a plus 5. If you can follow what I just did there, that's my trick for doing this division. If you want to do it a long way, you would do it via long division, formal method, and you would get 4 with a remainder of minus 4x plus 5. But either way, we have our expression now. And what we can see is, as x tends to positive infinity, well, this term, the fraction, is going to tend to 0 because the denominator is of a higher order, is x squared rather than x. But the denominator is positive, but the numerator is going to be negative. So overall, what you're going to have here is a small, very small negative quantity. So f of x is going to tend to 4 from below. That's the key point, from below. X tends to negative infinity. Well, the denominator is still positive, but now the numerator is going to be positive as well, of the fraction, and so we're going to tend to 4 from above. That's the key thing about the shape here that's going to help us with our plotting. Now, non-calc, and so stretching us with all of this, it's a full question, this one. We're going to do differentiation in order to find stationary points and points of inflection. So stationary points first. To work out dy by dx, I'm going to use the quotient rule. I'm going to use my split form of f of x here because the 4 is out of the way, and I've got a simplified fraction. So the quotient rule, v du by dx minus u dv by dx all over v squared. So in other words, v x squared minus 1 times minus 4, take away minus 4x plus 5 times 2x all over x squared minus 1 all squared. So v du minus u dv all over v squared using our quotient rule. And simplifying this, believe we have minus 4x squared plus 8x squared, so that's 4x squared. Then we have a minus 10x, and then we have a plus 4, and that's it. So a plus 4 all over x squared minus 1 squared. And so dy by dx equal to 0. Well, that implies that 4x squared minus 10x plus 4 is equal to 0. And just saving you a little bit of space here, if I divide by 2 and then factorize, that is 2x minus 1 times x minus 2 equals to 0, which tells me that I have stationary points at x equals 2. X equals 2, and I go back to the beginning and I substitute that in and work it through. X equals 2, I believe I get y equals 3. And then my second stationary point coming from this term now is going to be when x equals a half. And, well, this one, I don't have to substitute it in because we already did that. If x equals a half, well, then I have my intercept. So stationary points at x equals 2, y equals 3, and x equals a half, y equals 0. Okay, running out of space really quickly here. I'm going to just try and do points of inflection. Oh, well, do you know what? I'm going to leave the points of inflection because the algebra is going to get a little bit complicated, and we'll just talk about it when we have our sketch. You will have to follow the guidance in questions you're given. Sometimes, in more complicated ones like this, you won't actually need to find the points of inflection even if they exist, whereas at other points in time, it'll be a crucial part of getting the marks, and you'll have to look at the questions and see what specific information they're asking for. Quite often they'll say things like label the coordinates of all stationary points and the points of inflection, which is pretty clear. Okay, let's have a look. Asymptotes first. We've got vertical asymptotes at using this information, x equals minus 1 and x equals 1. And then we also had this non-vertical asymptote at y equals 4, a horizontal one. And we learnt that our function is going to approach from below here and above here. We learnt that we had two stationary points. We had a stationary point at x equals 2 and y equals 3. So somewhere up here. And we have a second stationary point here. And we actually had a y-intercept at minus 1, so somewhere like this. So quite a bit of information here. One other thing we could have done, I guess, is we could look at this form and think, well, is my function ever going to cross this line y equals 4? In other words, is this fraction, the second part here, is this ever equal to 0? Because if it is, then f of x equals 4, and our curve is going to cross this line. And in fact, this does equal 0. This equals 0 if x is 5 over 4, so about 1.25. So in fact, we must cross that line somewhere here. And so I think we can start to see what's going to go on here. We have an asymptote that's going to come across and then connect with the second asymptote, the vertical one. Down here, this asymptote must come up and then go through this y-intercept and then hit this stationary point, which means it must come straight back down again because that's a stationary point. We have this asymptote crossing y equals 4 at 1.25, 1.254. And then this is a minimum point, a stationary point, and then we must be going up and hitting our asymptote over there. So labeling our key points here, we had 2, 3, and we had a half and 0. I think that's a pretty good job at sketching this function. Let's have a check back to Desmos and see if that's indeed what we were looking for. Here we go. And yeah, we can see it's pretty much spot on. By drawing these asymptotes in, we can see the behavior of the curve as we get large positive x and large negative x, and then we can see these stationary points pretty much where we drew them. In terms of points of inflection, given a little bit more time and given perhaps a calculator, what we would have found is that there is a single point of inflection where we change from very clearly a concave up graph to a concave down graph somewhere along this stretch here, and I think actually you put it in, it's about 2.85. So approximately here we move from being concave up to concave down. And in fact that must be the case, right? In order to get the behavior that we're looking at, in order to get an asymptote from below, this has to be concave down, and in order for this to be a minimum, it has to be concave up. So a single point of inflection. Okay, one final graph. It's a long video for today, I know that. One final graph for you to do. I want you to try and answer this question, pause the video, and then have a go yourself. Okay, so last one for today, I'm going to go through it now. Slight additional thing we have to do, it asks for a maximal domain, and of course what we're looking at there is the denominator, and we're trying to see when this is valid. We must have square root of x minus 1 defined, and that's also only defined for x minus 1 is greater than 0, so that x must be greater than 1. Therefore the maximal domain is x, where x is a real number and x is greater than 1. So that's what we're looking at, and our function f of x is x plus 1 over root x minus 1. And so let's work through the same tools that we've had before. So intercepts first. First thing, well, x equals 0 is outside the domain, so that's not going to yield any intercepts, but I am going to have an intercept. Sorry, no, I was getting carried away. Y equals 0 is only going to happen if x equals minus 1, but that is also outside the domain. And so I'm not going to have any intercepts. Next thing we could look at is asymptotes. So first thing, if we look at the denominator of the fraction, I must have a vertical asymptote when at x equals 1. And then we're going to use, for non-vertical asymptotes, we're going to use this idea of splitting the fraction. So f of x is going to be x over root x minus 1 plus 1 over root x minus 1. If we think about what happens as x tends to positive infinity, well then the second function is going to tend to 0 because the square root of a really large number is still a really large number, so this is going to be really small. And then this expression on the left, the x over the square root of x minus 1, well, for large x, this is going to be really, really close to square root of x, because x divided by root x minus 1 is very close to x divided by root x, and x divided by root x is just root x. So the little bit of approximation, what we can see is that this is going to tend to square root of x. If you think about, well, is it going to be bigger or smaller than that? That's actually slightly hard for us to tell, because even though we're adding on something that's positive, this expression is going to be, well, it's going to be slightly smaller than square root of x, because we divide, no, sorry, it's going to be slightly bigger, because we're dividing by a smaller number. So we're dividing by a smaller number, so this is going to be slightly bigger, so this must tend to root x from above. Both those facts mean it has to be above, so that gives us a nice little fact. And then, of course, we can go into our stationary points, and we can do our differentiation. So, using the quotient rule again, I'm going to have x minus 1 to the power a half, take away x plus 1 times, differentiating the denominator here, a half x minus 1 to the power of minus a half, and all of that is going to be divided by x minus 1, because it's the square root of x minus 1 squared. And yeah, gosh, simplifying this is a little bit of work. A shortcut is, well, here's how we should do it. We have the half, which I can rewrite as a 2 on the denominator here. And then I have x minus 1, and here I have x minus 1 to the power of minus a half. So if I also write this as something times x minus 1 to the power of minus a half, I can put the x minus 1 to the power of a half also on the denominator, meaning this is going to be to the power of 1.5, because it's the x minus 1 to the power of 1, and the x minus 1 to the power of a half. 1.5 is 3 over 2. This will give me x minus 1, and this, multiplying by the 2 as well. So this is going to give me 2 x minus 1 minus x plus 1. Yeah, that's correct. Take a little bit more time over it if you want to check it out really carefully. But simplifying this, this is what I'm going to get. 2x minus x is just x, and minus 2 minus 1 is minus 3. So this simplifies relatively nicely as x minus 3 over 2 times x minus 1 to the power of 3 over 2. So we have a stationary point when x equals 3. And substituting that in, x equals 3 is going to be 4 on the numerator here, and square root of 3 minus 1, so square root of 2. So 4 over root 2, which is the same as 2 root 2. Yeah, 2 root 2. Okay. I could go on and look for points of inflection, and indeed, if you've done that, it's a little bit of algebra. But d2y by dx squared, the second derivative, well, that's 7 minus x over 4, x minus 1 to the power 5 over 2, just cutting the steps. So what you get is a point of inflection, only 1, when x equals 7, and if you substitute that in, you get 4 root 6 over 3. So what does this look like? Well, we have our function. We knew we were only defined for y equals 1. Sorry, x equals 1, greater than x equals 1. So we're only looking over here. And we know we have this non-vertical asymptote of y equals root x, which we know the shape of. And we know we're going to tend towards that from above. And then we know we also have a stationary point at 3, 2 root 2. Just checking whether we're above or below the line here. Square root of 3 and 2 times the square root of 2. Square root of 3 is definitely smaller than 2 root 2. You check that by squaring them. So this, if I square the 2 root 2 here, that gives me, what, 8? And so I'm going to have a stationary point that must be above. Coordinates of this are 3 and 2 root 2. And probably not the most helpful place to put it, but my function must come down. It must have a stationary point here, and then it's going to get closer and closer to this asymptote y equals root x. So I was going pretty well up until this point, and then this is obviously a little bit wobbly, but you can check it out on Desmos and just see exactly what it looks like. But if you're going to plot it on Desmos, also plot the function y equals root x, so you can see the behavior of the asymptote as it gets towards it. Okay, super long video today, but hopefully helpful to have me talk through my thinking as I'm plotting these graphs and sketching them. You'll get loads quicker and loads better at it the more you do. Be really precise, because in the exams, as we've talked about already with some sketching that we've done, the markers are really, really pedantic and really specific about the curves. Stationary points have to look like stationary points. Points of inflection have to look like points of inflection, and you can never cross your asymptotes unless you're supposed to. So, best of luck with it, and once you've tried the questions, let me know if there's any you really struggle with. All the best.